Picture a 16-year-old hunched over a circuit board at midnight, debugging Python code that controls the robotic arm she's programmed to sort recyclables by material type. She's not playing around. She's building the exact skills that solar installation technicians and automation engineers use every single day. I'm Chloe Miller, and I've spent years testing robotics platforms to figure out which ones actually prepare teenagers for real engineering work, not just another screen-based game. Welcome to the STEM Lab podcast. Quick heads up before we dive in. Everything you're about to hear, the research, the product testing, the recommendations, that's all done and verified by real human authors. But the voice you're hearing right now, that's AI generated. Just wanted to be upfront about that. If you've been listening for a while, thank you. Really, it means a lot. And if you're new here, great to have you along. We release new episodes every Monday, Wednesday, and Friday, covering sustainable engineering, climate-forward STEM education, and hands-on projects that actually matter. Let's get into it. The best robotics kits for teenagers bridge the gap between guided learning and professional-grade tooling. They teach ROS integration, sensor fusion, and mechanical design principles that translate directly to careers in sustainable manufacturing and renewable energy infrastructure. After testing dozens of platforms with varying power budgets, ecosystem lock-in, and real-world durability, I've identified the kits that genuinely prepare teens for industry-standard workflows. Now, let's talk about what you should actually look for in robotics kits for teenagers. You want your teenager learning the same tools they'll encounter in engineering internships and university labs. Look for kits supporting Arduino IDE, Visual Studio Code, or Python environments, not just proprietary drag-and-drop interfaces. The VEX V5 system, for example, runs C++ and Python, the exact languages used in automotive robotics and manufacturing automation. Check whether the platform supports ROS, which is the robot operating system, and the standard and professional robotics. Operating system flexibility matters too. Kits locked to iPad-only apps create dependency. Cross-platform support, including Windows, Mac OS, Linux, and ideally Raspberry Pi, builds long-term capability. Connectivity determines expandability. UART, I2C, and SPI protocols let teens integrate third-party sensors. These are the same communication standards used in environmental monitoring stations and precision agriculture robots. Cloud-dependent platforms disappear when companies fold or change business models, so prioritize kits with robust offline functionality and open-source firmware options. I've seen too many promising teen projects abandoned because a required app vanished from the App Store. Generic age labels like ages 13 and up tell you nothing. What you need are concrete capability checkpoints. Can your teen calibrate a PID control loop, program computer vision object detection, design and 3D print structural components that interface with standard fasteners? The best robotics kits for teenagers map to recognized frameworks like FIRST Robotics Competition Standards or VEX Tournament Specs, which provide external validation of skill progression. Look for kits that explicitly transition from block-based to text-based coding. Platforms supporting both Blockly and Python let teens bridge that gap without switching hardware ecosystems. Skill building should follow this arc: basic actuation and sensing, then closed-loop control, then multi-threaded programming, then CAD integration, and finally systems-level debugging. You want documentation showing what a teen builds in month 1 versus month 12 with quantifiable outcomes. Teenage robotics projects consume serious energy. Battery chemistry matters for both performance and sustainability. LiPo packs deliver high current for motor-heavy builds, but require fireproof charging bags and balanced chargers. NIM alternatives are safer but heavier and less energy-dense. Some platforms, like the Lego Spike Prime, use rechargeable battery hubs with built-in management. Convenient, but proprietary. Wall power requirements vary wildly. Industrial-grade arms might need dedicated 12-volt supplies, pulling 5 amps or more. Check that your home's STEM lab setup can support the draw without tripping breakers. I've run solar-charged projects off modified power tool batteries with remarkable success, but that requires understanding discharge curves and voltage regulation, exactly the kind of real-world electrical knowledge teens should learn. Connectivity infrastructure extends beyond USB. Wi-Fi-enabled platforms like ESP32-based controllers or Raspberry Pi integration open doors to IoT applications and remote sensing, crucial for citizen science projects and environmental monitoring. Bluetooth adds wireless debugging. Ethernet ensures low-latency control for time-critical applications like balancing robots or drone stabilization. Teenagers break things. They also improve things. You need robotics kits for teenagers built for both scenarios. Aluminum extrusion-based systems like VEX or Rev Robotics withstand repeated assembly cycles far better than plastic-only kits. Standard hole patterns like 8mm grid or half-inch pitch let teens integrate laser-cut acrylic or 3D-printed components, essential as they transition toward custom engineering projects. Check fastener standards. Metric M3 and M4 screws and nuts are globally available and cheap to replace. Proprietary connectors lock you into expensive replacement parts. Motor mounting should accept industry-standard shaft diameters like 3mm, 6mm, or 1/4 inch, so teens can upgrade to higher torque or more efficient motors as projects scale. Consumables add up fast. Calculate the total cost of replacement batteries, broken sensors, stripped gears, and annual software subscriptions. Some platforms require cloud credits for advanced features or annual competition registration fees. Others are genuinely one-time purchases with a lifetime firmware access. Examine the manufacturer's track record. Companies that sunset product lines strand users with orphaned hardware. Open source platforms mitigate this risk. If the vendor disappears, community support continues. The Arduino ecosystem has thrived for nearly 2 decades, precisely because it's not dependent on a single corporation's business decisions. Moving on to our top picks. First up, the VEX V5 robotics system. Check the show notes for a link to the current price. This delivers tournament-grade engineering in a surprisingly accessible package. You're getting metal structure, a multitasking V5 brain running free RTOS, and compatibility with C++ and Python, the exact stack used in industrial automation. I've watched teams use this platform to prototype warehouse sorting systems that mirror Amazon Fulfillment Center logic. Here's what works. You get industry-standard programming with full C++ and Python support and Visual Studio Code integration. The construction is robust metal, aluminum C-channels, and steel fasteners that survive hundreds of assembly iterations. There's an extensive sensor ecosystem, optical shaft encoders, vision sensors, inertial measurement units, all use standardized ports. It aligns directly with VEX Robotics competition standards, which provides external skill validation. And it's got cross-platform compatibility, Windows, macOS, and Linux software support with no cloud dependency. Here's what doesn't. The smart cables are proprietary. Replacement cables are expensive, and you can't substitute them with generic alternatives. There's battery lock-in. V5 battery packs cost around $80 each, and you'll want 3 for serious development. The initial learning curve is steep. Documentation assumes familiarity with object-oriented programming concepts. Real-world specs? It runs on a 7.2-volt proprietary LiPo battery, programs via USB-C, and has Wi-Fi and Bluetooth connectivity. The modular metal construction supports unlimited expandability with standard 8mm grid spacing. No subscription required. One-time purchase with lifetime software access. Next, the Rev Robotics Spark Max Expansion Hub with FTC control system. Check the show notes for a link to the current price. This targets teams serious about first tech challenge competitions, but works brilliantly for any teen ready to work with Android Studio and Java-based robot control. This is the kit I'd choose if your teenager wants to understand distributed control systems. The Spark Max motor controllers run onboard PID loops, offloading computation just like modern electric vehicle drive systems. What's great? Brushless motor support. Spark Max controllers enable efficient high-power motors used in aerospace and EV applications. It's Android-based programming, so the Robot Controller app runs on standard Android phones, teaching mobile development alongside robotics. The software stack is open source, built on Android open source project with active community development. Professional CAD integration is included. Official Onshape libraries teach parametric design with real mechanical constraints. And the power distribution is modular. Hot swappable battery connections and circuit protection mirror industrial practices. What's not? You need to supply your own Android phone, which adds $100 to $200 if you don't have a spare. Initial configuration is complex. Network setup and driver station pairing frustrates beginners expecting plug-and-play. Limited block-based coding. It's primarily Java and Kotlin focused, with minimal Blockly support for transition learners. Practical details: 12-volt battery, USB and Wi-Fi control, I2C, UART, and analog sensor ports. Aluminum extrusion frame with metric fasteners. Requires Android 6.0 or newer as robot controller. No mandatory subscriptions, but FTC competition registration costs around $275 annually per team. Now, the LEGO Education Spike Prime expansion set with Python integration. Check the show notes for a link to the current price. This surprises skeptics who dismiss LEGO as elementary level. With MicroPython support and Bluetooth connectivity, this platform teaches proper computational thinking while maintaining the rapid prototyping advantages of modular construction. I've used Spike Prime hubs to prototype environmental sensor networks before committing to custom PCBs. The iterative speed is unmatched. The advantages: dual programming environments, smooth transition from block-based Scratch to MicroPython text coding. The hub is rechargeable with USB-C, so no battery replacement costs. 5-hour runtime on typical projects. Strong cross-curricular applications, particularly for data science projects and renewable energy experiments. Tactile mechanical design builds spatial reasoning before moving to CAD. Extensive expansion compatibility integrates with Technic and Mindstorm's components for mixed media builds. The drawbacks: plastic structural limitations, not suitable for high torque applications, gears strip under heavy loads. Proprietary connector system means you can't easily interface with non-LEGO sensors or third-party electronics. Limited computational power. The hub processor struggles with computer vision or complex multitasking. Tech rundown: rechargeable lithium-ion hub with USB-C charging, Bluetooth 4.2, 6 I/O ports for LEGO sensors and motors. Cross-platform app works on Windows, macOS, iOS, Android, and Chromebook. Fully offline capable after initial app download. The Arduino Engineering Kit Rev 2 with MicroPython compatibility. Check the show notes for a link to the current price. This is purpose-built for teens ready to transition from kits to custom hardware design. You're getting 3 university-level projects: a self-balancing motorcycle, a mobile rover, and a whiteboard drawing robot. They teach PID control, sensor fusion, and inverse kinematics. This is the platform I recommend when teenagers start asking, how would I build this from scratch? Why it's good. Industry standard Arduino Nano RP2040, compatible with thousands of third-party shields and sensors. Comprehensive online course included. The curriculum maps directly to undergraduate mechatronics syllabi. Real engineering challenges. Projects teach actual control theory, not simplified toy versions. Open source ecosystem means infinite expandability with community libraries and tutorials. Multiple language support, C++, MicroPython, and Arduino Sketch compatibility. Why it's challenging. Assembly precision required. Mechanical tolerances demand careful construction. Rushed builds perform poorly. Limited structural components. You'll need to supplement with 3D printed parts for custom projects. No mobile app. Desktop IDE only, not suitable for teens who prefer tablet-based workflows. The details. USB powered during development, 5-volt battery pack or wall adapter for deployment, I2C, SPI, and GPIO expansion. Mechanical components use metric M3 fasteners, Windows, macOS, and Linux compatibility. No subscriptions, full access to Arduino Cloud free tier included. The Ya Boom Raspberry Pi 4 AI robot with computer vision. Check the show notes for a link to the current price. This represents the bleeding edge of educational robotics. This is genuine AI and machine learning hardware running OpenCV, TensorFlow Lite, and ROS. Your teenager programs object detection, face tracking, and autonomous navigation using the same frameworks deployed in warehouse robots and agricultural drones. It's technically demanding and occasionally maddening, which makes it perfect preparation for actual engineering careers. The strengths: full Linux environment, native Python 3, complete development toolchain, SSH access for remote debugging, computer vision capabilities with a 1080p camera and hardware-accelerated OpenCV for real-time image processing. ROS integration lets you learn the robot operating system used in academic research and commercial robotics. Access to the full Raspberry Pi ecosystem means thousands of tutorials, libraries, and community projects. Genuine AI and machine learning training. Run neural networks locally with no cloud dependency for machine learning inference. The challenges: significant setup friction, requires comfort with Linux command line and package management. Power hungry. Raspberry Pi 4 needs a dedicated 3-amp USB-C supply. Battery runtime under 2 hours with active processing. Cooling requirements. The processor throttles without active cooling during intensive vision tasks. What you're working with: Raspberry Pi 4 with at least 4 GB of RAM, micro SD card storage, dual USB-C power, one for the Pi and one for servos, Wi-Fi and Bluetooth connectivity, compatible with all Pi hats and expansion boards, offline capable after initial software setup, free access to TensorFlow and OpenCV libraries. Finally, the SparkFun Inventors Kit with Arduino and Environmental Sensor Bundle. Check the show notes for a link to the current price. This pairs beautifully with add-on environmental sensors, creating a platform that bridges robotics and citizen science. I recommend this path for teenagers interested in climate monitoring, water quality assessment, or urban air quality mapping. You're teaching embedded programming while collecting genuinely useful environmental data that contributes to public datasets. Why it's excellent? Exceptional documentation. SparkFun's tutorials explain not just what to do, but why it works. Breadboard-based prototyping teaches proper circuit design before moving to permanent PCBs. Sensor ecosystem makes easy integration with CO2, particulate matter, and water quality sensors. No prior experience required. Project progression assumes zero electronics background. Open hardware design, all schematics published, which encourages modification and experimentation. The limitations: fragile prototyping connections. Breadboard wires pull loose easily, not suitable for mobile robots. Limited mechanical components. Focuses on electronics, so you'll need separate structural materials. Arduino Uno processing limits. 16 MHz clock struggles with multitasking. Complex projects need board upgrades. The specs: USB powered at 5 volts, 14 digital I/O pins, 6 analog inputs, 3.3 volt and 5 volt regulated outputs for sensors, Windows, macOS, and Linux IDE support, fully offline capable, no subscriptions. Let's tackle some frequently asked questions. What programming languages should teenagers learn through robotics kits? Teenagers should start with block-based languages like Scratch or Blockly to grasp computational logic, then transition to Python for its readability and industry relevance in data science and automation. By late high school, exposure to C++ for performance-critical applications and Java for Android-based robotics rounds out a competitive skill set. Python dominates renewable energy system programming, machine learning pipelines, and scientific computing, skills directly transferable to climate tech careers. C++ appears in embedded systems, aerospace, and automotive applications where execution speed matters. The best robotics kits for teenagers support multiple languages on the same hardware, allowing progression without equipment changes. Do robotics kits for teenagers require expensive annual subscriptions? Most quality robotics kits require no subscriptions for core functionality, but some platforms charge for cloud features, competition software, or curriculum access. VEX and REV systems offer lifetime software with one-time hardware purchase. Lego Spike Prime includes free apps with no ongoing costs. Arduino and Raspberry Pi platforms are fundamentally open source and free. Budget around $0 to $50 annually for optional cloud storage, advanced vision processing credits, or competition registration if your team pursues organized robotics challenges. Avoid platforms that lock essential programming tools behind subscription paywalls. That's a red flag for long-term viability. Calculate total cost of ownership, including batteries, replacement parts, and expansion sensors, rather than focusing solely on initial kit price. Can teenagers use robotics kits to prepare for STEM competitions? Absolutely. Many robotics kits are explicitly designed around competition standards like First Tech Challenge, VEX Robotics Competition, or RoboCup Junior. Competition preparation teaches deadline management, technical documentation, and collaborative engineering far more effectively than solo projects. VEX and REV platforms align directly with tournament rules and constraints. Arduino and Raspberry Pi platforms dominate maker competitions and science fairs. Competition Robotics develops interview-ready portfolio pieces that demonstrate problem-solving under constraints, exactly what engineering internships and university admissions committees want to see. Even if your teen doesn't pursue formal competition, building to competitive specifications ensures projects meet real-world performance benchmarks rather than just good enough to work once. How do robotics kits integrate with 3D printing and CAD design? Modern robotics platforms increasingly expect 3D printing integration for custom brackets, sensor mounts, and structural reinforcements. VEX and REV publish Onshape and Fusion 360 CAD libraries with standard mounting patterns, letting teens design parts that interface precisely with kit components. Spike Prime's modular nature benefits from 3D printed adapters that convert Lego connectors to standard metric fasteners. Arduino and Raspberry Pi platforms almost always incorporate custom enclosures or mechanical linkages. Learning parametric CAD design transforms teenagers from kit assemblers to genuine product designers. They're not just following instructions, but engineering solutions to self-defined problems. Budget around $200 to $300 for a capable FDM 3D printer if you're serious about robotics. What safety considerations apply to teenage robotics projects? Teenage robotics introduces hazards absent from earlier STEM activities. Lithium polymer batteries can catch fire if punctured or overcharged. High-speed motors with exposed shafts can catch hair or clothing. Soldering requires ventilation and heat management. Power supplies exceeding 12 volts present shock risks. Establish clear lab safety protocols covering eye protection during mechanical assembly, fireproof charging bags for LiPo batteries, and proper fume extraction for soldering or 3D printing. Require your team to write risk assessments for each new build. Identifying potential failures and mitigation strategies is itself a critical engineering skill. Most serious injuries in teen robotics come from complacency with low-voltage systems. 12 volts can deliver dangerous current through skin resistance under certain conditions. Here's the verdict. The robotics kits for teenagers that earn space in your home lab are the ones that scale with ambition. Platforms that support crude first builds and elegant senior thesis projects on the same hardware backbone. VEX and REV dominate if competition robotics appeals. Arduino and Raspberry Pi ecosystems win for teenagers interested in custom sensor networks and environmental monitoring. Lego Spike Prime bridges the gap for visual learners who need tangible prototyping before committing to code-first workflows. What matters most isn't picking the best platform, but rather choosing the kit that aligns with your teenager's trajectory towards specific industry skills. The 16-year-old programming automated solar panel cleaning systems needs different tools than the one designing autonomous reef monitoring rovers. Both paths are valid, both require genuine technical capability. Both build climate tech careers. Start with the kit that makes your teen excited to work past midnight debugging, because that drive, not the specific servo motor or microcontroller, determines who builds the sustainable infrastructure our future desperately needs. That wraps up this episode of the STEM Lab podcast. Thanks for spending this time with me today. New episodes go live every Monday, Wednesday, and Friday, so there's always something fresh coming your way. If you got value out of this, I'd really appreciate it if you'd leave us a 5-star rating and write a quick review. It genuinely helps other people find the show, especially parents and educators looking for solid STEM resources. And hey, hit subscribe or follow so you get notified the second a new episode drops. Talk soon.